Hi again. We're talking about Le Chatelier's principle. But let's first of all talk about escalators. Now, not just any old escalator, but an escalator that you are on. Not only any escalator that you are on, but an escalator that's actually driving up, and you rebel, are working your way down. Now, I want you to not race the escalator and see if you can get down before it gets you up. I want you to walk down the escalator at the same speed as the escalator is going up. You're going to stay put. You're moving, the escalator's moving, but for an observer, they can't see you actually move. Okay, you got that picture? All right, somebody at the mall says, I'm going to show this kid, and speeds up the escalator. What's going to happen? Two things are going to happen. Number one, there's going to be a moment where you go up because you're not moving as fast as the escalator. But then you realize what's happening and you speed up. Not to the point where you're on your way back down, but to the point where you are now holding steady at that new spot. Now we can do examples like this again. Or what if you go faster than the things like that? We're not going to bother with that. What I want you to understand is that both you and the escalator are moving, but there's no overall motion. And two, if the escalator changes, you're going to respond by also matching its change. If the escalator slows down, you don't need to go as fast. Now that is Le Chatelier's principle as it applies to escalators. And what's Le Chatelier's principle as it applies to chemical reactions? Well, this is what Le Chatelier actually said. And if I'm mispronouncing your name, Henri, I'm sorry, but we're going to call you Le Chatelier. That's Le Chatelier's principle. Now what I want you to do is I want you to think about what we know about reactions already. We know that for reactions at equilibrium, we put the concentration of the products on top of the concentration of the reactants. We know that it's dependent upon temperature. We also know, by the way, that temperature affects the rate of a reaction. That's important. Equilibrium is where the rate of the forward reaction, how fast is the products being produced, equals the rate of the reverse reaction, how fast are the reactants being regenerated. And we also know that the rate is influenced not only temperature, as we just reminded, but also by concentration. So if I start changing things that are connected to this equilibrium expression, I can start changing the reaction. Okay, what's going to happen here, and for the next few, is that there's going to be some detailed explanation, and then there's going to be a summary. But we're going to start by changing concentration. You don't really need the detail stuff, but you do want to know the summary. So if I take a reaction like this, if I add more reactant, more of the carbon dioxide, the only thing that can happen is that I now have more carbon dioxide available to react. The rate increases. Okay? If that happens, then I'm going to increase the concentration of the products because the reactants are going to react to make products. So if I increase the concentration of the reactants, it goes up here, it's going to drop down as those reactants make products, and the products are going to go up. Okay? Now, if I had a system at equilibrium and I add more, so I'm starting here and I'm putting it up, I might not drop back down to the original point. I might come down just a little bit, but the reactants will decrease, not to or below the original level, but they'll decrease from the amount that I added, and the products will increase. Okay? I'm going to then establish a new equilibrium with new concentrations, but there will be a difference. All right? So the equilibrium constant might be the same, but the equilibrium amounts will be a little bit different. So temperature dependence of K for the equilibrium expression. So if I'm at the same temperature, I should end up with the same value of K, but the numbers on top, the numbers that I'm using in the fraction will be different. Okay. Summary is the part that you do want to have. If I increase the concentration of something, the reaction is going to try, the equilibrium is going to try and get rid of it. Okay. If I increase something, it's going to try and decrease something. Do I decrease it by making more products, or decrease it by making more reactants? If I decrease the concentration, well, if I lose something, the equilibrium is going to try and replace it. Okay. Whoops, sorry, let me go back in case you're still doing that. Okay, the next thing I can do to stress a system, to apply a change to a system, is changing the temperature. Now again, details, you want the summary for sure. Details are a little bit optional, but they're why the summary works. If I have an exothermic reaction, the heat is produced. The heat is kind of like a product. It is certainly not a chemical. Don't say that it's a product. It's produced, it's released. If I have an endothermic reaction, the heat is consumed. It's definitely not a reactant because that's a chemical, but it's consumed, much like reactants are consumed. If the system is at equilibrium, if I cool it down, what's it going to try and do? Well, it's going to try and warm itself back up again. If I heat it up, it's going to try and cool itself off. And that's how the equilibrium is going to respond. It's going to shift to either warm up from a cool down or cool off from a warm up. So as a summary, and this is the part that's important then, is if I add energy, it's going to shift to absorb energy. If I release energy, or I pull energy out, then it's going to try and replace it. Kind of in the same, it's going to show the same behavior as it did for concentrations, except now we're talking about energy. Okay. Changing gas volumes. A lot of reactions do involve gases. Gases that are produced, gases absorbed. Maybe the whole thing is in the gas state, maybe it's not. Gases, though, are sensitive to volume because they occupy a large volume. So if I increase the volume of a container, if I increase the volume of a gas, increase the volume that the gas can occupy, it actually means I'm decreasing the overall concentration. So now it's a little bit like a concentration. The volume is going to be related to the number of moles of gas present, the number of moles of gas, that's going to be kind of key. And 1 mole of gas occupies 24.8 liters at standard ambient temperature pressure, SATP. Does that number matter? No, but that's true for any gas. 1 mole of oxygen, 1 mole of nitrogen, 1 mole of helium, 1 mole of nitrogen dioxide, and 1 mole of any gas occupies 24.8 liters at that temperature and pressure. So gases are gases, and that's kind of cool. All right, so if I take this reaction, notice that there are a total of 4 moles of reactant and a total of 2 moles of product. So if I were to do something like increase the volume, then what's going to happen is I have more space to fill. If I decrease the volume, I have less space to fill. So increasing the volume is going to cause the reaction to shift to the side that has more moles of gas. They can fill the volume better. Decreasing the volume, making them squishy. Now, what's the most efficient way to not crowd the space so much? Shift to the side that has fewer moles of gas. It must be moles of gas. And as I just said, what if I add a catalyst? Well, I know a catalyst is going to speed up a reaction. Well, a catalyst, what it does is it makes the reaction get to equilibrium faster, but it doesn't mean that the reactants are favored or the products are more favored. All it means is the whole reaction is going faster. It's going to reach that equilibrium faster. In other words, it is not going to have any influence on the position of the equilibrium. So it does not represent a stress applied to a system. What if I add an inert gas? I have a reaction involving, nitrogen and oxygen, and I start pumping in helium. That helium is not going to react with anything. What's it going to do? Really, all it does is get in the way. Now, I will increase the pressure. Now, this is where things get a little bit dicey, because if I decrease the volume, I increase the pressure. If I pump in a new gas, I'll also increase the pressure. But the inert gas, the gas that's not involved in the reaction, as I said, is getting in the way. It's interfering and reducing the overall effectiveness of some of the other collisions. So it has no effect on the equilibrium as well. Now, what was going to happen is in class we're going to take a look at this particular equilibrium. What I want you to do is make predictions beforehand. So here's the reaction, and your job before class is to predict the effect as I add different things to the system. These are the possibilities for what we're going to add. We're going to take one, we're going to add some water, we're going to add some more hydrochloric acid, and so on. You can read it just as well as I. We're also going to increase the temperature and decrease the temperature, but I didn't tell you exothermic, endothermic. Just another room. Okay. So that's your job for this in class. In the meantime, what's going to happen is we're going to work with Le Chatelier's principle. We're going to hopefully do some more lab work on that. The one I just showed you is going to be more of a demonstration to get our heads into it, and then we'll get some practice with it. All right, talk to you in class.